whatever pixel records is just an integral, right, over the wavelength.
Yeah.
And you start with your light that gets emitted, that gets multiplied by the transmission of medium wavelength, right? Then it gets bounced off the target, which has some reflectance wavelength, right? Then we go back to the camera, so we multiply it by the transmission of wavelength again. And then we integrate it. And then there's one piece, there's the camera responsivity function of wavelength. Right? So in the simulation setup, we can make our life easy because we can assume, well, we know the reflectance because it's a target that's we're calibrated. So we can assume that you know what this is. And we can assume that we know the light spectrum here as well. So this is known and this is known. And the camera we can calibrate, so we can assume that this is known as well. So all that is left that's unknown are these, right? Okay. So this is what's really known. So I think the whole name of the game is given this image pixel value P, right? And then you have P for red, green, and blue. And then you have C, R, G here, right? Given these values and all the known parameters, could you find a way to figure out what the TW is?
I have a question because
Yeah.
I'm curious. In the simulation process,
Mhm.
so we don't know this circumstance.
Oh, you do.
So,
Do you? No, you do. You said if you don't know it, you can't simulate, right? So you make certain assumptions regarding what it is.
yes.
Right. So when you're specifying simulation parameters, you're saying, okay, my water properties, the total absorption, you specify in terms of the absorption coefficient. So the T here will be equal to E to the negative distance times absorption coefficient of lambda. Because it depends on distance. So you know exactly what T is. Right? The whole point is, imagine that you're diving, imagine that you go diving, right? You dive underwater. You have your camera that you've calibrated, so you know this. You're looking at the known target, so you know this. And let's assume you know the light because you have a flashlight with you, but you know nothing about water. So the question is, how would you determine water parameters?
Oh, got it.
Now, I'm not going to ask you to go to the Arriaga Center and go diving to figure out what the water properties are. That's what we see. We have simulations. So when you're running the simulations, you're assuming certain parameters here.
Yeah.
And then you try to solve for those parameters using those measurements and see if those things are matching.
Oh, got it.
Right? Yeah. So ideally, when you solve your inverse problem for this parameter, you will be able to relate, you will be able to see, oh, I got some values. How do they compare against what I used for the simulation here? Does it make sense?
Yeah.
So in our, is this parameter known or unknown?
I think it's no.
It is known. It is known because
Then
that's.
if all of these are known,
No. I think
except this.
No,
right?
no, no. So when you're simulating, everything is known.
Yeah,
right?
yeah.
But then the question is, the simulation is meant to represent a model of the real world to simplify your life.
Yeah.
The scenario in the real world is as follows. You're going diving. You want to figure out what the water properties are. So you don't know what they are.
Yeah.
So you assume that in that system, you don't know what these are.
Yeah, but isn't it in this case, the only parameter we don't know is the total absorption rate. But this is known.
This is part of the simulation, right? Because at the end of the day, you're simulating the camera.
I don't know if my understanding is right.
Yeah.
So it's like there are two process. The one is simulation, and the other is the algorithm.
Exactly.
Yeah.
And in the simulation part, we know everything.
Yeah.
We know every like this one.
Maybe let's put it this way. In the simulation, you assume everything.
Oh, yes.
You're free to choose whatever you want.
Yeah.
Okay.
And then this is a nice way to put it, right? So here you have point first. You generate your data that you know exactly. And then in the second step, asking yourself, okay, if I assume that I know everything except for this, can I derive my unknown from all the stuff that I know?
Isn't it just a math
think it's like
mathematical.
math.
Yeah, it is a math. This one is just math.
Oh,
Yeah.
okay.
I think I
So we
can-
don't have to create our own algorithm or something like that.
Well, it's not as easy as dividing to numbers. So it is
Okay.
more complicated, and I think you've taken convex optimization.
Oh yeah.
Okay, then this is exactly what the tools you could use. I think the paper that I forwarded you is really relies on, or I did forward it to you.
I didn't get the.
Yeah.
We didn't get the article.
I did send it to you.
You did? Wait 1 second. I was.
So I actually wrote an article basically describing a method to derive something like TW. So you can take a look at how I did it in there and try to replicate the process.
Oh, okay.
In my case, I didn't have the ground truth because I actually had real water measurements. I was just screwing with it and making reasonable assumptions. But you know the ground truth.
Yeah.
So you can say, okay, this algorithm with this data can achieve this kind of accuracy with respect to those,
I know it.
right? So that's kind of the idea.
Got it. That's a real interesting topic.
Do you mind if you send me again? I couldn't. Do you know under which topic?
Is it like one of the earliest emails? Like the one that
I'm trying to
Okay.
see.
You know what? I can find it if you have access to IEEE.
Yeah, I do.
Okay, ooh, that's a lot.
Is the title a model for
Yes,
estimating
there it is.
spectral
Sorry.
properties?
Yeah, a model something. Yeah, a
The model
model
for
for.
estimating spectral.
Okay.
So you can take a look at this. You can take a look at this paper and the method that I used, to estimate those parameters. Now there are a few. So just to go to the paper, the setup was very similar to what you have here, except there was one minor difference. So in my case, imagine that this is the water surface. I was lowering a camera, and there was a target, and I was lowering both the camera and the height. So the distance here was varying. And I was taking pictures along the way. Sorry, the setup was slightly different. It was actually horizontal like this, right? And I was lowering.
Is the camera under? Oh, under the water.
Underwater,
surface.
yes, under the water surface. I was lowering on a piece of food. So the
camera is merged in the water.
Yeah.
Okay.
It was not in this. It was in a house. So here the difference was that I was taking pictures as I was going deeper and deeper underwater. So I could throw everything together and basically try to estimate things in layers. Right. So think of it this way: you take a picture with this much water, you estimate properties, and then you also assume that if you take a picture lower here, then the transmission is just multiplying this transmission. So you can build up a bigger system with several measurements, and you solve for everything at once.
Oh, got it.
which is just a slightly complicated setup that you have. You should be fine with this.
Yeah.
This should be, you should be able to figure out this use case, this how to solve for this setup.
Yeah.
One important question that you may think about is, well, so TW, so the transmission parameters, are a function of wavelength, right?
Yeah, yes.
So if you assume a certain discretization of wavelengths, typically every, let's say, 5 or 10 nanometers of the visible range, that means you get a vector in about 30-dimensional space, right? Which means to solve for the transmission, you'd need 30 numbers, really.
Yeah.
Are there ways to simplify it? Is there a lower dimensional representation, like maybe a set of basis functions that you could use?
Like using I forgot the name. Like using the multiplication of the matrix.
Yeah, so that's one thing you can think of as you can think about that, you know, maybe this really what really you're interested in is not T but the absorption wavelength, right?
Yeah.
Maybe that is really spanning some more like 5-dimensional, 5 basis functions.
Yeah.
And then you can have your absorption basis times absorption coefficients. So this is 30 by 5, this is 5 by 1, and that gives you your absorption of rate, something like that. So think about, is there a way to represent? Or maybe you can just impose a smoothness penalty as you're solving your system. Too quick?
Yeah, I think no, I need to figure out more deeply.
A lot of this stuff, I feel a lot of this stuff is here in this paper. So I suggest you give it a try, give it a read, and feel free to ping me, ask me questions. I'm happy to respond. So I think the first step would be really, so this is the intensity reduction as the light goes through. Think about what happens if you have scattering, right? Because absorption is one of the parameters, the other is scattering. So basically what happens in scattering media is you have a light goes from the source, but it doesn't really reach the target. It gets, you can think of it as reflected from the medium and goes into the camera. Okay, so think about how, well, maybe let me give you a hint. So really what's happening is you have your pixel value, right, is equal to the integral, as we said, of light times transmission times reflectance, right, times transmission again, and times the camera response function, d lambda. Okay, so that's the direct component. But then we also have another integral of light times maybe some other transmission times camera response function. So you can think of it as this light here.
Yeah.
Right. How would you account for this?
Do you mean how are we able to separate this?
Yeah, and whether you're able to. I'm just bringing it up as a food for thought. Maybe we can start with assuming that they only have absorption and see if you can manage with absorption, and then maybe part of the project would be, okay, if I have a purely absorptive medium with no scattering, this is how well I can do it. So some analysis, and then you can crank up a scattering component and see how well your algorithm behaves when you make the when you start to have a misalignment in your assumption that the medium is just absorptive versus it actually adding some scattering. Right? Maybe you can treat scattering just treat this as some constant p prime, right?
Yeah.
So you model your pixel as this a that's function of t of lambda, right?
Yeah.
Plus p prime.
Yeah.
So this is where you hide all your absorption parameters. And when you're optimizing, minimizing your thing, you're looking for this as well as this. Maybe not. I'm not sure. I don't know.
Is P prime in this case absorption or classing? 就是有很多
I think she meant scattering.
yes
Scattering.
scattering.
So this would be so this component actually contains information about scattering and absorption, right? Because you can really think about this as really all this stuff that got into the camera lens because the light ray was diverted by the medium. So you see there's no interaction with the target here. So there's no reflection part here of wavelength.
Oh, yeah.
Right? But the light still travels through the medium. So that's why you have this T prime component. So what I think happens if you assume that this is just a fixed offset that gets added to the pixel, you will, in a sense, throw away some information that could give you some hints about absorption and scattering properties. If that makes sense.
Yeah.
Right.
Yeah.
Because right now all the scattering is pretty much contained in this term. So you're saying, okay, there is some scattering, but how the scattering is behaving, you're kind of sweeping it under the rug and saying, okay, I'm not going to look into that. I'm just going to assume it's some additive part that's there, right?
Okay. But after we solve what p prime is, and can we just solve like this equation equals p prime and then solve what is t prime is, so that can get the property of scalar scattering.
Well, I think it's a little bit trickier than that because the p prime is not really coming from a single spot, because you could have another light ray going like this, interacted here, and then it bounced here. And then you can have another light ray here and here. So scattering is much more complicated, put it this way. So I'm only mentioning scattering to give you something to think about. I really believe that as the first step, just model and simulate things with no scattering,
Okay.
which you can do, and then try to solve for how much the transmission loss due to scattering.
Yeah. Okay. I see. And for the script, we're going to receive tomorrow.
So what I'm going to do is I'm going to write a script that will simulate this setup for some parameters, some reasonable parameters, right? So like distance, that's reasonable, field of view, water parameters that are reasonable. You all know this. And we'll generate a camera image here.
Okay.
And I'll save all the data so that you can look at exactly the script that generated it, the data, so you can start thinking about the solver portion. And hopefully, as you'll get your simulation going and the ability to render your own images, you can maybe vary you can maybe vary water parameters and see how to generate a little bit more data.
So what's the difference between tomorrow's script and the simulation we're trying to run on MATLAB? What's the difference?
Nothing. That's exactly the same thing, right?
Yeah, but isn't it we won't still able to run it?
Well, hopefully you'll be able you'll get access to one of the labs in the computer, and you'll be able to get it running from there.
Okay. I'm still confused. Then why we still have one more script from tomorrow?
Okay, so you've asked me to give you some data so you can start working.
Uh-huh.
I could just send you a MATLAB file, but I don't think this is going to be helpful. So I'm going to write my own script that generates everything, all the data. I'm going to run it myself, save the data, give you the data and the script, so you know exactly how the data was generated.
Okay, got you.
Make sense?
Yes.
Okay, good.
Okay.
So like
So that
in
once you
tomorrow's
finally figure out how to render stuff, you'll be able to take that MATLAB script and run it and hopefully get the same data.
Got you. What did you say?
Oh, so basically for tomorrow's script, you would just be like putting different parameters and to produce the outputs that we can use for calculating the absorption spectrum.
Yes, exactly.
Okay.
Except for in my script, I'm not going to render for different, let's say, absorption parameters, different. I'll just pick one, something that's reasonable.
Okay.
And that still require us to run on school's computer for that script.
Well, yes.
Okay.
Yeah. I mean, unless you can figure out this whole
Yeah, I mean, I would rather save some time just to run that.
I mean, I think it would be just allowing you to work in parallel. You can start working on the algorithms, and then once you figure out how to render, because yes, technically speaking, from the data I'll give you, you should be able to figure out for one test case, right? But it would be interesting to see how well this algorithm behaves if you have across a variety of conditions, right? So what if I give you just one water type? Will it perform equally well if the water type is different? If the distance is different? If maybe the camera signal to noise ratio is different? If light source is different, because you can see, well, maybe there's a daylight source, maybe you have some other light source. What happens there? But these things should be fairly straightforward. Once you set up your solver and you know how to go from data to solver, you can just run these things, generate the data, and so forth, and run some kind of analysis.
Yeah. So do you have any other questions?
It's pretty clear for me this moment.
Okay.
Yeah.
Okay. Right. Good. I can leave it with you.
Oh, yes. Thank you.
There's some stuff on the other side, but don't and yeah, I'll try to get this done by tomorrow.
It's okay because we are only able to access school computer on Monday earliest. We can
Really?
Because David needs to be on campus.
Okay.
So yeah.
Okay, good. So I have a little bit of time. I'll try to get it done.
It's okay. Yeah. Thank you.
Yeah, of course.
Yeah, thank you. Bye bye.
Bye bye.